Hello everyone. So we are going to be working into some circular motion problems, helping ourselves get ready for tomorrow, where we'll be dealing with banked curves that do have friction. That's where we're going, but today we'll keep on with banked curves that don't have friction. So let's take a look at just some circular motion problems and some tips that we can have for solving them. Starting off, uh, draw a free body diagram. Make sure it's clear, make sure it's obvious. That is always number one. Afterward, you should assign your axes. It's always easier if you assign your x-axis to be the direction of the acceleration. And this way that you don't have to find components for acceleration. If you make your acceleration the x-axis, then that means your net force is in the x-axis. And any forces that have components that are perpendicular to that have to cancel out because there is no acceleration except in what you have just defined as the x-axis. So I know that we've been doing things on inclines and we've rotated our axis so that the x-axis is parallel to the slope. That may or may not be useful depending upon what's happening. Always ask yourself, where is the acceleration, and assign that direction to be your x-axis. That's going to be something that'll help you out quite a bit. And then remember that centripetal force is not a force that actually goes on your free body diagram. Centripetal force is net force. So whenever you write F net, you could just replace it with F centripetal. So let's take a look at three examples and see how they work. So the first example is a vertical loop. If I have a 3.3 kilogram mass attached to an 0.75 meters of string, and we whirled it in a circle on the Earth, and it completes one spin in 1.3 seconds, can I determine the tension at the top of the swing? So ignore that math. Right now, look at that diagram. That diagram there has the tension force and the gravity force at the top of the swing. The rope would be pulling it down, and gravity is also pulling it down. So now we can look at our math. My net force equation, or my centripetal force, should equal all the things that make it go in the direction of acceleration. Which direction is the acceleration at the top? It's accelerating straight down because all of our circular motion has the acceleration going to the center of that circle. So at that moment, the acceleration is straight down. So our centripetal force is equal to the tension headings down and the gravity additively, because the gravity is also heading straight down. So those are additive. And in this case, I know that there's mass times acceleration. The m part is easy. Centripetal acceleration is either v squared over r, but we don't actually have the v. So I'm going to use the 4 pi squared r over period squared format to solve for the acceleration. And that's equal to my tension plus, and we'd find gravity with m times g. Bringing it over, right, solving for F tension, we would see that it is our centripetal force mass times 4 pi squared r over period squared, and we would subtract out the force of gravity. In this case, at the very peak of the swing, the tension would be about 25.4 newtons. I just plugged in my numbers after this. Feel free to double check my calculator work. I think I got it right, but mistakes happen, whatever. Feel free to double check that. That's how that. But this is how this one should work. Hopefully, you feel comfortable then you're like, okay, my centripetal force is directed into the center. That's down. Tension and gravity are both pointing down. They're working together. They add, and we can solve for our tension because that's the only variable we don't know. What if I ask for the tension at the bottom of the swing? Well, I would redraw my diagram. So again, ignore the math, look at the diagram. My object is now at the bottom of the string. My tension is pulling upward into the center of the circle. The gravity is always pulling down to the center of the earth. Since my net force, my centripetal force, is into the middle of the circle, so my tension is causing that centripetal force and it's being resisted by gravity. Ft minus Fg. And then from there, we can use the same numbers, so we use the same formulas, and we find out that the tension force, since now gravity is tension minus gravity, you move gravity over, it turns into a positive rather than a subtraction, and we find that the tension force should be 90.2 newtons. Again, feel free to take the time, plug in the numbers, double check my calculator work, but this is the process that we do. We've drawn a really clear diagram. We make sure we know which direction the acceleration is into the center of the circle, and we constructed a net force equation or a centripetal force equation that matches my diagram and my free body diagram there. So the vertical loop, you can see there are two distinct possibilities. When we're dealing with vertical loops, you have to make sure to keep your eye on which part am I talking about, and that will determine how you draw and what formula you make for this type of problem. Let's look at something like a horizontal loop for our next example. So here we go. You can see I have a little toy plane going attached to a string, and it flies around in a horizontal loop. When this toy plane flies in a circle, it's attached to a 1.5 meter long string that is attached to the ceiling, and when the string makes a 30-degree angle, there's 22.5 newtons of tension in the rope. So that's a number provided in there. So I'd ask, well, what is the plane's tangential velocity, or what is its circular or centripetal velocity? In this case, make sure you have a clear diagram and what forces are acting. Gravity is pulling it down, and the tension pulls in a line along the thing itself. So I've got myself a good, clear free body diagram. Now the next thing is I need to set my axes. Where will my x-axis be? Well, the acceleration is into the center of its path, that circle there. And the center of that path is a horizontal loop. So the horizontal is my x-axis because that's where the acceleration actually is. So if I set that, then I can split all of my x and y's into my x and y axis, where I've set x to the horizontal in this case, because that's where my acceleration is. So you can see in blue I've done F tension X, and in green I've done F tension Y. And now that I've split up my axes this way, I can go ahead and I can start my problem. So I'm splitting it to X and Y. I'm starting with my X axis because that's where things are going. My centripetal force is caused by the only X force is my tension force, so that's easy peasy. I'd be looking for velocity, so I'll use the mv squared over r formula is equal to, and that's going to be tension, and we see how it's opposite of that 30 degrees, so it'd be sine of the 30-degree angle. Trying to solve for velocity, I just did a little rearranging here, multiply it by r, divide by m, take the square root, and so I have tension times sine theta times r over m. I don't know the mass of this object. I don't know the tension. Oh wait, hold on. No, I do know the tension. I know the force of tension. The tension is 22.5 newtons. Oh, awesome. Okay, so tension is 22.5. That's easy. Sine theta, theta is 30. Do we know the radius of this situation? Hopefully somebody is saying yes in their head, if not out loud, because we see that the hypotenuse, that is the string, and then the x and y component are blue and green, actually makes a right angled triangle. We could find the radius by taking 1.5 sine 30. So we can find the radius. But, as I did say before, the mass is unknown. So I don't know what the mass is. But I do know that gravity is related to the mass. So since gravity is in my y-axis, let's take a look at what's happening in the y. So here I'll start with my net force equation for y. F net y is equal to the tension y pulling it up minus gravity pulling it down. Now, this object is accelerating horizontally. That means there should be no vertical acceleration. My F net y should equal 0. And if my F net y equals 0, then I'd have my tension cos 30 is my y component minus m times g, that's gravity, should equal to 0, and that allows me to solve for the force of tension in as a function of mass and gravity and the cosine of theta. So I can substitute Ft in there and just shove Ft from my y-axis and shove it into my x-axis formula. When I do that, I get my velocity is Ft, so mg over cos theta, that's what we got from our y-axis, multiplied by sine theta times r over m. Seeing how the mass is both top and bottom, those actually are going to cancel out. Very convenient. This is a situation that is mass independent. And I'm just left with gravitational acceleration, radius, and this sine theta over cos theta. For people that are not familiar, if you ever have sine theta divided by cos theta, that's actually something that we call an identity, a trigonometric identity, and sine divided by cos is tan. So I've simplified the thing in so it's just g times r times tan theta instead of saying g times r times sine theta divided by cos theta. Punch that in and I get 2.1. So remember it would be g, 9.8, radius, which we see is 1.5 multiplied by the sine of 30 times tan of 30. I hope I punched in the numbers right. It should be 2.1. Again, double check my work. So there's our horizontal loop. It's a little trickier, right? But if we've set up a nice clear diagram, we make sure to set our x-axis to be the same plane as the acceleration. In this case, it's a horizontal acceleration pointed into the center of that horizontal loop. We can split into x and y's, and the nice thing is that when we split into x and y's, we know anything in the y will have to end up equaling 0 because there should be no y acceleration. The net y, f net y, is always going to be equal 0 when we set it up this way. And that allows us to make some equivalences, that allows us to use some substitution and solve for things that we wouldn't be able to if we did it a different way. So that's why these 3 tips that we've been doing that I started, let's see where we're here it is. Draw your clear free body diagram, assign your axes, and remember your centripetal force is the net force. If you do those 3, you're on a good path. So let's look at one more problem. The banked curve. So we have a car and it's driving into a circular turn with a radius of 435. Did I change that? I did. Sorry, everybody. Change that to 235 meters. That I changed it in one of the slides, but I forgot to change it in the other slides. So we're going to remember that's a 235 meter banked curve, and it's banked at an angle of 25 degrees. So what's the velocity that this car needs to maintain to go through the turn without sliding up or down the curved road? Now, if we consider this, what would make a car slide up or down the curved road? Well, if this is a curve that has absolutely no friction, there's no mention of friction anywhere here. If we stopped the car, in other words, slowed it down too much, where does the car go? Hopefully, we're all saying, when you stop the car, it slides down the slope. And if you sped it up too fast, if you went too fast, remember your impulse or your inertia wants you to travel in a straight line, and if the normal force of the road isn't going to be large enough to totally account for all of that inertia, you'll actually end up traveling a straight line, which pushes you up the slope and off the edge if you go too fast. So going too fast slides you up the slope, going too slow slides you down the slope. We don't want either of those. We want to stay perfectly in the right spot. So this is our situation. I have 2 diagrams. The one on the left we see is kind of the zoomed out version showing it's a circular motion. And what we get to see from that is it's a circular motion. This is a horizontal circle again. It's a horizontal circle. And our diagram on the right, it's a free body diagram. You can see that there's our normal force done in the dotted line. Uh, the horizontal and the vertical lines are the x and y components respectively. And pulling down is the force of gravity, mg. In this case, why do we break things up this way? Well, it's because our acceleration is into the center of the turn. The acceleration was horizontal, so we choose our horizontal as the x-axis. This is actually, if we think about this, this is the exact same as the problem we just did with the toy. That it's a horizontal loop, there's gravity pulling down, and there's a force pulling kind of up and into the center of the circle. With the toy airplane, it was tension, but in this banked curve, it's normal force. So, so this actually should go very similarly. So here we go, everybody. I've adjusted my problem. I turned it into a radius of 235, not 435. There's our bank curve. And if it's the same, I'm going to start off the exact same way as I did before. My circular force is in my x-axis, so my normal force x is the only component in that direction. I put in my ft sine theta. I go ahead and solve for v. I notice I don't know. Oh, I have it as ft. I didn't change that to fn. There we go. See, it's so similar. I copied it and I forgot to change the subscripts. Whoopsies. Um, but we're in the same situation, so we hop over to our y-axis to check, okay, our f net y needs to be 0. It's normal y minus gravity. I, again, forgot to replace ft with fn. Whoopsies. But we solve it the same way, and so I don't want to spend too much time. It's the exact same math. We would go through it, get the same relation. The velocity going around a banked curve with no friction would lead us to 32.8 meters per second. Those are 3 examples. Hopefully, between the work that we started on Thursday and the work that we're doing today, you're getting yourself a handle on how circular motion begins. What will be happening tomorrow is tomorrow there will be an introduction of bank curves with friction, and that you're going to start similarly, but it throws a whole new piece in there, which complicates the situation and gives it a greater challenge. So tomorrow, bank curves with friction. Practice the homework today to get used to bank curves now, so that when you begin looking at it, you'll be able to draw your free body diagrams clearly, and you'll be able to work out all of the other things very nicely. Thanks very much, everybody. Have yourself a good day.